Hello everyone, it's a pleasure to talk to you today about description of domain of discontinuity for Anosov representations. I would like to thank the organizer for inviting me to give a talk and also for organizing this event. So in this first part of my talk, I want to explain, to define geometric structure in the sense of Klein and explain how one can associate to an Anosov representation, to some Anosov representation, a geometric structure. So in the first part, I will talk about GX structures and explain how in some case, in case of Fuchsian representation, we have a correspondence between representations and geometric structures. And then I will try to extend this to show how to extend this to Anosov representations. So first, I will talk about GX structure, which are geometric structure in the sense of Klein. So when I talk about a GX structure, I want to fix a Lie group G and a space X on which G acts analytically, transitively, and faithfully. So, for instance, 3 examples can be, for X, we can take R2 or H2, or RP2, or higher dimensional manifolds. But here I'm giving dimension 2 examples. And as a Lie group G, we can first take R2, acting on R2 by translation, to get a notion, which will help us define the notion of translation surfaces. We can take the isometric group of H2 to define hyperbolic structures. And you can consider PSL3R acting on RP2 to define projective structures. So now, once we fix a pair GX, if we have a manifold M, which is smooth and connected, we say that a GX structure on M is a way to model locally M on X with transition G. What it means is that it's a maximal atlas of charts which are diffeomorphism between some open sets UI in M and VI in X. And what we require is that if you have 2 charts that intersect, the transition map is locally the restriction of the action of some element of G, Gij. Okay. So once we have a GX structure on a manifold, we can associate a couple of objects to this GX structure, which are the holonomy and the developing map. So first, the developing map. If we have so the GX structure gives us way to locally model M on X, but by gluing the maps together, we can get a map from the unicell cover of M into X, which is called the developing map. And one can define also the holonomy. So the developing map is well defined up to post-composition, is uniquely defined up to post-composition with the action of an element of G. X. Okay. And we can define the holonomy. So to do this, if we have a loop, let's take a non-trivial loop on M, we can lift it to M tilde, the universal cover, and then we can map it through the developing map in X. And then we can look at a chart from the base point of the loop going to the beginning of the path, and another chart from the base point of the loop to the end of the path. And the transition map between the two is some element that I will call holonomy of gamma, which is an element of G. And so these procedures define the group morphism between the fundamental group of M into G, which will well define up to conjugation by some G in capital G. So if we change the base point of X we took, we will post-compose the developing map and we'll conjugate the holonomy by this element G. So these 2 maps satisfy some equivariance property with respect to one another. So with this, we can ask the following question: which representation arise as a holonomy of a GX structure? So if you have a geostructure with a representation, and ask when can we go the other way around. So now we start with a representation rho from a discrete group into G, and we wonder if we can construct some GX structure associated to this representation, whose holonomy is this representation, or is related to this representation. For this, we want to construct a domain of discontinuity in X. So what we want a domain, omega, that is rho of gamma invariant, and we want also that rho of gamma acts freely and properly discontinuously. So properly discontinuously is the right condition to ask, to have that omega mod rho of gamma is a smooth manifold. And so if omega is a connected domain of discontinuity that is not empty, we get a GX structure on the quotient, because the quotient is just a quotient of a part that is modeled on X because it's X. So it's locally modeled on X naturally. And this GX structure is such that the developing map, its image is equal to omega. And the holonomy is almost rho. So if omega is simply connected, the holonomy is rho. But if it's not, then we just have that this diagram commutes. So the interesting part of the holonomy is equal to rho. So let's take an example. For instance, let's take consider hyperbolic structures. So SO21 is the isometry group, is isomorphic to the isometry group of H2, or the group of orientation preserving isometries of H2, more precisely. So we can take a regular octagon in the hyperbolic plane H2 with angles 2 pi over 8. And if we do so, we can glue this octagon by the following identification given by these 4 colors, arrows. So this defines a representation of a group generated by these 4 elements into SO21. So it's not a free group, it has a relation, which is a product of some commutators is 0, is trivial. And so if we take omega to be the whole of H2, the action of this group will actually be properly discontinuous, and the quotient of H2 by the action of the group will give us the closed surface of James 2. So here, the holonomy of the hyperbolic structure we get on this surface will be exactly this representation rho. So that's an example of a geometric hyperbolic structure on this, a GX structure on this surface and its holonomy. But more generally, if we take a surface group, so the fundamental group of a surface is closed, orientable, of genus G, where G is at least 2. We have a correspondence between hyperbolic structure, which was just SO21 H2 structures on the surface, and the holonomy map defines a correspondence between this space and the space of discrete and faithful representation, which are called Fuchsian representation. This means that any Fuchsian representation is the holonomy of a hyperbolic structure on SG and vice versa. So for this theorem to be complete, I need to quotient by the right action on the right and the left. So hyperbolic structures here, we consider that 2 hyperbolic structures on the left are equal if they differ, if they can be obtained from one another by a diffeomorphism that is isotopic to the identity. So sometimes we consider marked hyperbolic structures. GX structures are often considered marked structures. And on the right, we need to quotient by the action of SO21 by conjugation. The holonomy we get are only defined to conjugation. So this is a nice correspondence, and what I want to talk about now is how to get such correspondence for all the spaces of representations and all the kind of geometric structures. First, I want to talk about convex projective structures. So consider a representation rho 0, which is the composition of first a function representation, which maps a surface group gamma G into SO21. And then SO21 is a subgroup of SL3, R, so it can be mapped into PSL3R. And so what happens is that on RP2, if you look at the space of isotropic lines, it's an ellipsoid here, this circle, that is preserved by SO21, and so in particular it's preserved by rho. And actually the inside of this domain is actually the Klein model for the hyperbolic plane. So by the same reason as previously, omega is a domain of discontinuity for the action of rho, and its quotient defines a projective structure whose holonomy is rho 0. We get a projective structure on the quotient, which is a surface SG. And an interesting fact is if we deform rho 0 to represent rho in gamma G into PSL3R, if we continuously take at least a local deformation, one can prove that there is still a convex set that is preserved by rho, and we can do, and the action on the inside of this convex set will still be proper, and so the representation is still the holonomy of a projective structure on the surface. And actually, Choi and Goldmine proves that the space of, if you take the space of projective structures on SG that are convex, so convex means that the developing map of M of the initial cover of SG is properly convex, means it's convex and compact in some affine charts. Then it corresponds via the holonomy map to the space of Fichtean rotation, which is the space of deformations of rho 0. So the whole connecting component of representations that can be deformed to the representation of rho 0. And so that's an interesting expansion of the previous correspondence. And we'll see that actually these representations are Anosov. So that's already, So we're already extending to more general Anosov representations. So Fuchsian representations, they satisfy, not only are they discrete and faithful, but it turns out that they also satisfy some strong dynamical properties. And so these properties can be generalized for representation of surface group, not only surface group, but actually also more general hyperbolic group, but today we'll be interested in surface groups still, into any semi-simple group. So the representations that satisfy these properties are called Anosov representations. So we can add the following questions. The question, are Anosov representations the holonomies of some GX structure on some compact manifold M? So it's harder to get a compact manifold. It's getting non-compact manifold is not too complicated, but here we want a GX structure on a compact manifold. First, I want to say a few words on the geometry of gamma. We consider the Gromov boundary of the group gamma, which is a topological space naturally defined associated to the group gamma G on which gamma G acts. And so rather than defining it, I want to just give a description of it. If we fix a Fuchsian representation, the group will look like coarsely will look like the hyperbolic plane. And so we can identify the boundary, Gromov boundary of the group with the boundary of the hyperbolic plane. And the action of gamma g here will just be the action of rho of gamma g in the boundary of H2. And so this space with a gamma g action, this pair is independent, it does not depend on the choice of rho we have. And so this is a way to consider this Gromov boundary. So it's just a circle on which rho of gamma g acts. And moreover, it has a property that if we take a point gamma, a non-trivial element gamma in gamma g, it will have its action on the Gromov boundary will be a Anosov action. It's in particular, what will have an attracting fixed point and a repelling fixed point, gamma plus and gamma minus. Point. And so these attracting fixed points will be dense in the boundary, Gromov boundary. Now, rather, so I don't want to define the Anosov representation, but I want to give an important consequence, a property of these Anosov representations. And so let rho be a k Anosov representation in PSLNR. So in PSLNR, there is not only one Anosov property, but we have we can say that the representation is k Anosov for some k between 1 and n minus 1. More generally, we need to that corresponds to a choice of a maximal parabolic. And so we say, so if the representation is k Anosov, then a consequence is that we have a unique continuous rho equivariant map, psi k, or sometimes psi k rho, to emphasize correspond to the representation rho, from this circle, which is the boundary of the group, into the Grassmannian of k planes in Rn. So space of k dimension subspace of Rn. And it has a property that if we have gamma in gamma g, gamma non-trivial, remember that gamma plus is the attracting fixed point in boundary of gamma, then its image will be the attracting fixed point of rho of gamma. So so in other words, if you take any gamma in gamma g, rho of gamma will have an attracting fixed point in the space of Grassmannian of k planes. And if you draw all these attracting fixed points, the closure of this set will be a circle if you draw the attracting fixed point for all elements of gamma g. And so, for instance, each representation in PSL square, there are actually 1 and 2 Anosov. And so the first boundary map is a circle of lines, which is just a circle in RP2, which is actually the boundary of the convex set that is preserved. And the second boundary map is a circle of planes, which is a circle of projective lines in RP2. And the circle consists on all lines tangent to this convex, which is actually a C1 convex. And so Guichard Wienhard and also Kapovitch and Porti constructed many domains of discontinuity for Anosov representation in flag manifolds. And for various notion of Anosovness. So here I'm writing one example that is easier to state. So if we have an Anosov representation in PSL 2NR, so we need we need to be in even dimension, we can consider the domain in the flag manifold RP2n-1. So we want to construct a projective structure. And so we take RP2n-1 and we want to have a domain of discontinuity. We want to remove, for instance, attracting fixed points of elements of gamma g. And actually the right condition, the right set we want to remove to get a co-compact domain of discontinuity is we want to remove all the projectivization of all these n planes that are in the boundary map. And if we do this, then omega is a domain of discontinuity, and the quotient of omega is compact. So, for instance, what could happen, what happens for some Anosov representation when n equal 2, you could have the boundary map to be a circle of planes, operative lines in RP3 that follows a ruling of some hyperboloid. And so the domain omega rho in this case will be the complement of this hyperboloid. And okay, in this case, it's a bit special because it has two connected components. If you want to have a connected domain of discontinuity, you can pick one of the connected components. And so this theorem helps us get some correspondence between geometric structure and Hitchin representation in PSL-NR. So we say that the representation in PSL-NR is Hitchin if it can be deformed as previously as a representation that is the composition of something function and the irreducible representation of PSL2R in PSL-NR. So here recall that PSL2R is isomorphic to SO21. It's an exceptional isomorphism. And there is only one irreducible representation up to conjugation in PGL-NR. So this is analogous to the definition I gave previously of Hitchin representation in PSL3R. And Laborie proves that Hitchin representations are Anosov with respect for any k in between 1 and n-1. And so using the previous theorem, Guichard and Wienhard proved that the space of Hitchin representation in PSL2NR is in one-to-one correspondent via the holonomy map with a connected component of the space of projective structures on M, which is omega rho mod rho of gamma, for some and hence any representation rho that is Hitchin. The smooth manifold M does not depend on rho. Or so omega rho mod rho gamma or some connected component of omega rho mod rho gamma. Okay. And so another way to use this domain of discontinuity is more generally if you have any n-Anosov representation, and then it is the holonomy of a projective structure on omega mod rho of gamma. And actually this is non-empty when n is at least 2. And when n is at least, and this is connected for n at least 3. So if it's not connected, then we need to take one connected component of it to get a projective structure. But in this corollary, and also in the previous theorem, it's not clear what is the manifold M. And so with Daniele and Kunglingli, we prove that if we have a Hitchin representation in PSL2NR, the manifold M, which is this omega rho mod rho of gamma, is a fiber bundle over the surface with fiber a Stiefel manifold, which can be described as On mod On minus 2 cross O1, but can also be described as, so it's as the intersection of two quadrics. And so instead of getting structures on the surface, we get structure on the fiber bundle of the surface. And so in the part 2 of my talk, I want to describe this theorem, proof of the theorem, and some generalization of it. Thank you for your attention and see you in part 2.